My name is Holden Marceaux, and I'm here to present about the results from experiment 3, the refrigeration or air conditioning cycle. So a little bit of background. We have our ideal cycle. Starts at 1, goes across the compressor. Refrigeration is brought to a higher temperature in the compressor at ideally constant entropy. From 2 to 3, high pressure refrigerant rejects heat across the condenser. From 3 to 4, the refrigerant is brought down to a lower pressure, ideally at constant entropy, across this throttling valve or capillary tube. And then from 4 to 1, the low pressure refrigerant goes across the evaporator where it's able to absorb heat or energy because it's at a low pressure and low temperature, and then repeats the cycle. This is our ideal versus real change in entropy with charge. This right here is the percentage of the original charge, so 100% is fully charged, 80, 60, 45. 45 is the lowest. As you can see, it's not the same as the ideal cycle. The biggest difference here is from 1 to 2, which would be across the compressor. This is basically just saying that at a lower charge, the compressor produces more entropy, and it's just less ideal, and that's what's most affected by the reduction in charge. But other than that, we have approximately, approximately the same results for everything else. The only other main difference is from 4 to 1 across the condenser because we are actually gaining temperature, so the temperature and entropy increase. And then this is the effects of change in charge with enthalpy. And over here we have our pressure enthalpy graph. And you'll notice that this graph is a lot more similar to the ideal graph than the previous one was. This is mostly because enthalpy is not heavily affected by the change in charge like entropy is. It's just this is our performance trends. I've got all over the place for my coefficient of performance, but all of them are less than 1. This is mainly because it's a very small system and it's not running a whole lot of charge. But our coefficient of performance is calculated using QL, which is the heat absorbed in the evaporator, divided by the work done by the compressor. So basically, it's what we want to get out of the system divided by what we have to put into it to get that. And here you can see some of our actual calculated values. Our heat absorbed, which is what is actually used to rate the tonnage of the unit, is 2.35 tons about. We projected about 5.37 tons of heat and had to put in about 18 horsepower approximately. The reason heat rejected is always going to be higher than heat absorbed in a cooling unit like this, that's the extra energy comes from the input to the compressor. And our max flow rate for the system for almost all of the charges. I didn't put the fully charged had a lower mass flow rate, and I didn't put that for some reason, but for all the other charging conditions, it had almost exactly the same mass flow rate. And this is how we calculated some of these things. First off, our mass flow rate of R22 is calculated using this equation. And the way we got this is by setting the heat absorbed by the evaporator down here equal to the heat rejected from the air that's flowing over it. And this HE and HI would be the enthalpy at the exit and inlet to the duct that the air flows through over the evaporator. I found these numbers using the dry and wet bulb temperatures. And the mass flow rate of air I found using this equation, which is the velocity of the air coming out of the duct times the cross-sectional area divided by the specific volume of the air coming out of the duct. Everything else heat rejected is this H1 is the enthalpy coming into the evaporator, and this H4 is the enthalpy going out of it. H2 in the power consumption is the enthalpy coming into the compressor, and H1 is the enthalpy coming out of it. That's it. Any questions?